So without further ado, let us proceed to the programme, and it's a pleasure to introduce our first speaker, Professor Gerry Gilmore from Cambridge, and his title is Gaia, the six-dimensional Milky Way map is coming to you. Gerry.
Thanks very much. That's about slide number 20, if we could go somewhere nearer the start. While he's finding that, let me comment that for purely accidental reasons, we're on our way back from the headquarters of BIS, where Gaia has been on display for the last 3 weeks. And so I have in my pocket about 20 Gaia badges, now, which I will provide. Now, I don't know, the relevant description is, I don't know the technical term, but whatever is the opposite of casting pearls before swine would be appropriate. Here they are. So now, let me go on and talk about this amazing mission Gaia, which you'll see, and as we go through in the slides, is underway. The tagline is 1 billion pixels for 1 billion stars. It's a huge camera in space. There's the rocket. It's producing 3 different fundamental sorts of data. There's images, which are being turned into both precision photometry and precision astrometry. Spectrophotometry from about 3,500 to 1,000 angstroms, so across the entire visible band, and resolution 12,000 spectroscopy around the calcium triplet for the brightest stars. And so this triplet of information is what we are using to try and understand what is our local universe like and how to set up a map of the sky. And this is the map of the sky. The first Gaia data release came out mid-September. And this is its map. This is the first high-precision map of 1.1 billion objects on the sky. It's not quite complete. There's patches and complexity. This is a test data set that we worked very hard to get out just so that people could get a flavour of what's in Gaia. The real stuff will be out the next big release in early 2018. But already from this you can see a flavour for the magnificence of what is Gaia. And so I'll first of all just run a few slides through, say what Gaia is and why Gaia is, and then show you the sort of thing that we're doing with it. And this is the reason that Gaia exists. If you want to know a good reason to spend €1 billion, then the answer is the elephant in the room that you've forgotten about. And the elephant in the room for astrophysics is that we've got no idea where stuff is. Many people in this room and all of my colleagues talk about doing percent precision cosmology. And percent precision cosmology is based on good distances for a few hundred stars. And so you can work out what root n is, if you like, just for that for a start. And what the calibration is. I think there are 5 Cepheids in that number. And so you can get Nobel Prizes on the basis of 1% cosmology from that. But if you want to do astrophysics, then you need to do something about solving this problem. And it's a hard problem. Because measuring distances to stars is the single challenge that mankind has had, as far as we know, for as long as recorded history. And the reason it's not been done is that we didn't have one of these. And this is Gaia, so there's some of the numbers down here on both sides. But this marvellous piece of technology, delivered and built by several people who are in this room, actually, is the highest precision optical bench ever created and put into space, and the highest stability as well. And it's a truly remarkable piece of kit. It's just a ring of silicon carbide, this new wonder, super stable, super temperature invariant material, with 2 5mm telescopes hanging on it and feeding a single optical bench that I'll come to. The key, this is the science case really for all the things one is doing, but the key reason for needing Gaia is that fundamentally space is big. And because space is big, stars are far away. So if you want to measure the distances to stars through parallax, you need to measure very small angles. And for that reason, this is the precision that Gaia is doing. If there are any engineers in the audience, you'd recognise this as a very small number indeed. What it corresponds to is measuring the centroid of a stellar image with a precision that's comparable to bisecting a human hair seen from 1,000 kilometres. 1,000 kilometres from here is the top of the Swiss Alps. A more homely example, for those of you who aren't mountaineers, is that it's measuring the thickness, and you can tell from my accent why this is homely, it's measuring the thickness of a human fingernail seen from here when that fingernail is in Sydney. So it's across the Earth. Or 2 centimetres on the moon, but nobody knows how far away the moon is, so I've never found that a useful analogy. There's some fascinating software challenges and some spectacular hardware involved, for which we are spectacularly grateful to our industrial partners, many of whom are in the UK. But first, let's remind you what you see when you look at the sky with high resolution. Look at the sky as a function of time. What you see as a function of time, and this is a measurement for this particular star, this is a simulation of what our sun would look like from 20 parsecs away. And what you see, first of all, is proper motion as the star goes across the sky, and the proper motion is related to galactic dynamics, gravitational potentials, and so on. Then you see this cycloidal parallax on top of it, caused by our motion, and measuring that angle gives the distance. And then you see that these simple models don't fit the data. Stars wiggle all over the place, and that's because they're planets. And so as well as knowing the space motion of the star and the distance of the star, you also know its planetary environment. And so this is what Gaia is doing for a very large number of sources indeed. In fact, you'll have noticed on that first picture, and I'm sure you all instantly understood why, there are 2 telescopes on Gaia. I'm sure you just cracked that instantly. And the reason is that if you just have one telescope and you look in a direction, all the parallax ellipses, all the parallax vectors all line up. And so you can only ever measure a differential parallax. You can never do anything absolutely. But if you have 2 telescopes, you're using at the same time with a known angle between them, then that gives you the extra information you need, the extra angle between this and that, to solve for both separately. And that angle is simply what we call the basic angle. It's the physical angle between the 2 telescopes. And for Gaia, that's at 106.5 degrees. And so this allows us to get absolute parallaxes, something that is impossible from the ground. Actually, it's more complicated than that because you've got 2 telescopes and everything's moving in all sorts of directions. And so actually handling the data is a very complicated challenge indeed. And that is why Gaia is a sort of paradigm of modern space missions in which about half the money, little less actually, about 40% of the money is spent on software. So software is just as expensive and difficult and takes a lot longer than hardware. The hardware just blows your mind. I mean, it's awesome stuff, but the software is pretty impressive as well, actually. There's a lot more of it. Now, any real-world system, the people who build spacecraft, our friends in Stevenage and Cheltenham and so on, they're really clever engineers. They're really startling. And what they realise is that they're solving challenges is what they find interesting. And therefore, solving challenges was obviously what we would find interesting, so they put a few challenges in just to keep us alert. And the challenges they put in were, first of all, some scattered light, which shouldn't be there at all, but nonetheless there is some. And in fact, we've learned how to mitigate this through careful optimization of the way we read out the focal plane, and also just by continuing the mission for a few extra years so we can get the signal back, so that won't be a problem at all. The next thing was a bit of ice on the mirrors. That shouldn't be there either, but clever engineers knew it was going to happen, so there were heaters. And so here you see transmission as a function of time. So there's ice building up on the mirrors. You turn on the heaters, do it again. The most recent heating event was in August this year. There might be one more needed, so that's a solved problem. This one is kind of interesting. They're things we call microclanks. These are mechanical relaxations of stresses inside the spacecraft. And it was known these were going to be a big challenge from Hipparchos. And in fact, what you see here is the spin rate of the spacecraft versus time. And the spin rate is critical because the spin rate is what we have to use to work out where the stars are. What we actually measure is time and flux. And we have to convert time into where the spacecraft was pointing at that time. And so we need to know this. And so these little glitches, and these are mechanical relaxations that gently stretch out over a metre or 2 on the sun shield. And they do things like this to the spin rate. And we were very worried about these, but just in the last few months, it turns out that they're actually very well behaved mechanically because there's a real mechanical structure model gone into this. And so they're soluble as well. None of this is in the first data release, but I can tell you that we're actually way below spec in doing this stuff. And then there was this big challenge. The whole point about Gaia is absolutely stable basic angle. In fact, it's not stable at all. This is the basic angle as a function of time. And this fluctuation here corresponds to about 1 milliarc second, which is 1,000 times bigger than the Gaia spec, so you need to know it accurately. But just to put that, and we can, but just to put that in perspective, we don't know where this fluctuation is coming from. It's probably just a dressing of the entire 4 metres of metal that's, not metal, 4 metres of ceramic that Gaia is made from. But if you assume that what it is a physical movement of one of the primary mirrors tilting, and these are 1.5 metre mirrors, that mirror is tilting by an amount that's equivalent to 1/10 of a helium atom. And the very fact that we can measure that is astonishing, but that tenth of a helium atom corresponds to this signal is awesome. So in fact, the precision with which we're doing stuff is larger than that of the ground-based gravity wave detectors. It is astonishing. Fortunately, someone had enough sense to put on board Gaia the highest precision interferometer system ever built, just as a backup, and it turned out to be quite useful indeed. So anyway, there are challenges, but all of these challenges are met. You won't see the benefit of those in the present data release, but 18 months from now, we're confident that we're going to be ahead of spec in everything. It's really going well. And this, of course, takes a lot of people. This is the author list on the first Gaia release paper. Somewhere in there you'll find me in small print. But for those who are into nerdy things, this is the scale of the challenge. What we have to do, if you really want to produce a six-dimensional map of the sky, is invert a 10 to the power 13 matrix. And that, it's easy to calculate. If we assume Moore's law carries on at its present rate, we will be able to do that in approximately 2,000 years from now. So it requires a little bit, you either hope that your pension lasts, or you can either do some clever things. And so people are doing clever things, and it's this very, very intelligent, massively sophisticated algorithm development gone on here, involving a lot of people. Actually, this is just the author list. The appendix has another list equally long of the engineers who built the thing. And that's something I'd really like to keep emphasising. Gaia exists because 500 really clever engineers did brilliant work. The rest of us have just had to clean up what they gave us. That's easy by comparison. So here's some of the first stuff that's coming out of it. This is an image of the focal plane. This is how Gaia works. This focal plane is big. I guess, hope you can see the numbers. It's nearly a metre long, 1/2 metre wide. It's bigger than a coffee table. It's a big focal plane, biggest one ever put in orbit. And as a star comes along, well, it's actually the focal plane that's moving, but imagine a star's coming along, it tracks across, and little electronic windows are set up and track across the main imaging part, the spectrophotometry, and the spectrograph and radial velocities. And all this stuff is what we process in Cambridge. Here's the pipeline. I won't go through it at all, but here's the results. This is the precision with which we currently are calibrating Gaia data. And I'm sure you can't see it, but so this is magnitude along here from 5 to 21. So it's quite a big dynamic range. And in case you can see it, this is 1 millimagnitude here. Okay? So every star in the sky brighter than magnitude 16 has delivered sub-millimagnitude photometry, and every one of those stars has already been observed over 100 times. And this is better precision than the best that's possible from the ground, and we're already doing it routinely, and we can do better. And we'll go brighter as well. So this was done by my colleague Dafford Evans in Cambridge. So it's working. The system's going really well. This is what they use to do it. There are people who actually enjoy looking at these boxes with flashing blue lights. And they cost an awful lot of money, but nonetheless, I have a lot of boxes with flashing blue lights sitting in a large cold room in Cambridge, churning away, thanks to the Space Agency. And this is what they produce, okay? So the classic way in which we present the sort of information is the HR diagram. So brightness of stars. This is the first ever HR diagram. It wasn't published till 1920 in this form. This was a review article by Russell, but actually this sort of Y shape, bright at the top, faint blue and red, was actually, everybody thinks this was the beginning of US astrophysics. It was actually developed for the first time in Cambridge, where Russell was a postdoc. And Russell just wrote this stuff up as a postdoc in Cambridge. So this is a UK discovery, this HR diagram. But nonetheless, he, like all bright postdocs, snaffled it for himself and built a career on it. This is the Hipparcos one with 100,000 stars, and that's what we have now. Now, this is a mere 2 million stars. A year from now, we'll have 1 billion. This is just a wee taster, just to show what you can do. So these are just the brightest 2 million stars in the sky. And so that's just the number density. This diagram here I've colour-coded by space motion, or proper motion actually, but space motion. And so you can see immediately that these high-mass young stars, the high-mass young stars are very low space motion. You can see the age of the universe just cutting in here. Here's the old stars with higher velocities. You can see this amazingly complicated structure up the giant branch. None of that is actually predicted or corresponds to isochrones. So there's a huge amount of discovery space waiting going on to find out what on earth is going on here. What's this stuff, for example? This stuff's the Cepheids, of course. And so there's a huge amount of information, and I'll show you a couple more examples of that later on. But this is what we have for now, just as a wee taster. Here's one of the wee tasters a lot of people are interested in. Is well, there was this famous Pleiades distance anomaly. What's going on? Well, here is on the left-hand side here is the distance to clusters from Hipparchos, and here's the new ones. We call them T-gas for this thing. The agreement is absolutely superb for all clusters except the Pleiades. And the Pleiades has moved from there to here. And so this is now, Pleiades now agrees with all the other astrophysical determinations. We have absolutely no idea why. Something strange happened in Hipparchos, and until we understand that, we're not going to be completely comfortable with Gaia, but nobody's had time to look at it yet. But nonetheless, that Pleiades anomaly has gone away. This, in fact, is where we are. This will be submitted for publication in a few weeks. This is where we are now with the cluster diagram. So what's plotted here is the parallax from parallax versus the parallax deduced from the proper motion modelling of a cluster. So this is resolving out, what this means is that what we're now doing is resolving out the internal 3D structure and the internal velocity dispersion profile of the nearby open clusters on the sky. You can no longer talk about the distance to a cluster because we've resolved them out. You have to talk about the distances to individual stars, and the difference between talking about the distance to a cluster in terms of accuracy are these blue dots and the red dots. So if you start talking about individual stars, suddenly you're doing 3 times better. And that just means that everything in the local universe is now resolved in 3D. We no longer have distances to things with an NGC name. It has no meaning. And here's a bunch of the clusters all piled up. This is just using public Geneva photometry. If you do it using our internal Gaia spectrophotometry, the individual clusters have no scatter at all. So each individual line, I'm not allowed to show you that, unfortunately, but the individual lines have no scatter at all. But this sort of slightly odd structure, this very broad region here in the HR diagram, why is there such a lot of width in the HR diagrams before the turn-off? We don't, it remains to be seen what's going on there. But it's not obviously consistent with our current understanding of stellar evolution. So this will be available for you in a few weeks' time, but it's just astonishing how much one can do with just piddling 2 million stars. Of course, I mentioned the elephant in the room's distance scale. So here's the distance scale. So here are the period luminosity relations for Gaia, Cepheids and Aralaires. These are the Aralaires in the Magellanic Clouds, the ABs and the Cs. You see they line up very nicely. Here's some light curves. So here, just for illustration, this one is the Cepheids. So this is the Cepheid period luminosity relation from Hipparchos. This is what we had until 6 weeks ago, and this is what we've got now. And you can see the scatter's gone way down. Next year, by the time we're able to close the loops, the error bars will be smaller than these individual data points. And the number of data points will go up from 400 to a few thousand. And so then we can start doing serious things. You can see the same thing over here for Aralaires, again, Hipparchos versus Gaia. So you can see this is just the first stage, but the improvement is spectacular. And here are the Gaia PLC relations for the Cepheids. And again, this will be available fairly soon. One of the other sort of interesting sort of results, you can say, well, let's go out a bit further. So here is a zoom in on that picture I showed you right at the start of the small Magellanic Cloud and 47 Tuc, and there's Omega Cen, just to show you how much dynamic range there is in the whole thing. But this is an interesting example of how the world was waiting for Gaia. This paper was submitted to the archive AstroPH 6 hours after the Gaia data race went public. So the people were all set up and ready to go. It's a bunch of Americans. And what they've done is looked at the mean proper motion as a function of position on the large Magellanic Cloud. And these little lines here are proper motion vectors. And you can see just by eye, looking at it, you can see the large Magellanic Cloud rotating. So this is the first time in the history of mankind we've actually seen an external galaxy rotate. And that's based on 14 months data. In 14 months data, you can see it rotating. This is the proper motion of the centroid, the space motion of the whole thing. But just in 14 months data, you can actually see the LMC rotating, even though its rotation period is 10 to the 8th years. And that gives you an idea of the Gaia precision. We're talking about 10 to minus 9. precision, and that's what you can do when you've got 10 to minus 9. So in a couple of years' time, we'll see M31 rotating and M33. So our entire local universe becomes a 3D structure with real kinematics. Totally awesome. There's a vast amount of other stuff you can do with Gaia, but in 20 minutes I can't even mention all the topics. I've just listed a few of them here. Two of them of particular interest are extrasolar planets. I showed you in the beginning that everything with a high mass planet, anything greater than about Saturn or Neptune probably, will be seen, every system will be seen. So we expect to see 70,000 systems, based on known statistics, of nearby stellar systems with Neptune or heavier planets. That's 70,000. And interestingly, this, of course, because we have distances to the stars that have planets and the ones that don't, this is a volume complete sample, so we can do proper statistics for the first time ever on what's really out there. And if Gaia has continued as we hope it will be for a decade, we'll actually be able to find solar systems like our own for the first time ever. There's something way out there with decadal periods. So we'll have 70,000 of those. And then there's solar system bodies. Gaia has so far observed about 30 tracked orbits for about 35 million asteroids in solar system bodies. There'll be about 250,000 new ones, we think, because the main belt asteroid population was pretty well known anyway. The new ones are interesting, particularly because Gaia is out beyond the Earth and is looking back in. So Gaia, for the first time ever, is doing a study of the asteroids that potentially Earth-killing ones, the ones that are up during the day, the ones that you cannot find by looking at nighttime because they're between us and the sun. And so we'll have the first ever survey of potentially Earth-destroying asteroids, and then lots of GR and fundamental physics and things. Now, my last couple of slides, I'd just like to say that one other thing we're doing, really important, is real-time astronomy and outreach to the public. So we have this website in which all of our Gaia science comes out. We produce every day a map like this of new transients that weren't there yesterday. You can download an app, get these things on your phone if you're young enough to have a smartphone. We have programs running in schools. So here's a school that's in East London where these kids actually have been doing follow-up of Gaia sources, get light curves for them, tell us what they are, learning how to do science by doing science. And this, my last slide for the summary, is a nice example of what the sort of thing we're finding. This is the first microlensing event found in the galaxy away from the galactic bulge. It's out in some field in the Milky Way. This is the second one. And this is going on right now. It's a binary microlens of a star, 13th magnitude star up in the night sky right now. And here's a zoom in on the light curve. Because it's so exciting, we have approximately 10,000 observations. The global community of amateur astronomers and school kids has adopted this object. And so they're all following it for two reasons. First, it's bright as hell. It's 13th magnitude, so they can do it. And second, the best fitting model of this thing actually includes a 10 solar mass black hole. There's big error bars on that. And we'll know the solution to the error bars when we get to this second caustic crossing. And that happens next Wednesday afternoon. So this is something that's going on now. A 13th magnitude star in Cygnus is going to vary between 14th magnitude and 11th magnitude over an hour. And either is going to discover the first 10 solar mass black hole or tell us that it isn't. Either way, but don't know. But next Wednesday afternoon is the time for you to go out and have a look in Cygnus. This is bright enough. You will see it changing by 3 magnitudes over half an hour. You can see it by eye. This is an example of the sort of stuff we're discovering as a bonus for free, and we're giving out, trying to give out to the public. Well, we would, except we have no money for outreach, nag to the space agency. But anyway, leaving that aside, Gaia is a triumph. We're ecstatic, we're thrilled. Here's a little summary of the ridiculous numbers. Just to put this in perspective, just in this 25 minutes I've been talking to you, Gaia has measured 100 million positions. Thank you.
Just one word, wow. And I would just like to take the opportunity to acknowledge also Gerry's personal commitment to the project over many years and for leading the UK effort on Gaia. Right, questions, comments? Okay, let me start. I don't see any hands there.
Somebody right at the back, but yeah.
I'll start anyway.
Yep.
Several times you acknowledged the part played by industry, by engineers, could you just I think you said some of them are here, so
Yeah.
perhaps you could acknowledge the...
Yeah, Ralph. Where is Ralph from Airbus? There is Ralph from Airbus. Airbus were the prime contractors. Airbus Defence and Space, as they're now called. And so Airbus Toulouse, but particularly Airbus Stevenage, they did the clever electronics on board, so all the smart work there. E2V in Chelmsford built the CCDs, which are the heart of Gaia. The precision control system was built in the UK, and the onboard software control system was built in the UK. And then, of course, there's Fabio and his mates who funded all the thing at ESA, and we're totally indebted to his Sicilian charm.
And what about the faceless bureaucrats at the UK Space Agency?
You mean the ones who don't give me any outreach money?
Yes. Okay, yes.
So what is the status of dark matter distribution of Gaia at the moment?
Okay, we don't know. The initial delta release from Gaia was only the bright stars, and although there are giants in there that go a long way away, statistically the sample is useful for dynamical analyses only out to 100 parsecs. And inside 100 parsecs, one of the things we have discovered in Gaia, in fact I think it's on the next slide, is that there's a huge amount of kinematic substructure in the local part of the Milky Way, driven by spiral arms, the bar, whatever, dynamical history. And so the system is so far from being fittable by a simple distribution function that we can't say anything useful just yet. We need a longer baseline. That longer baseline will come in the next data release when we can go out to a kiloparsec and fit through some of this high frequency structure. At face value, the numbers look remarkably like those that were first published in 1989 by me, actually.
What are the brightest objects that you measure?
Yeah, there's no limit. Well, there is. We can't see the sun, and you should see what it looks like when Venus goes through the focal plane. But no, all stars. So there's a special observing mode. So the normal standard scanning mode works up to magnitude about 5, but the brilliant engineers at ESA worked out a way of doing special little scanning modes, fundamentally looking down the diffraction spikes a half a degree away from the star. And so even Sirius is having its parallax measured. We haven't quite worked out how to process those data yet, but they are being taken under the assumption that we'll crack it eventually. So we can go from, we can go from -1.5, which is Sirius, and the completeness limit at present is about 20.7. It's a lot fainter than expected. So the goal was 1 billion stars. We're actually going to have a complete sample of 2 billion, partly because we've gone fainter and partly because it turns out there are a lot more stars on the sky than we thought there were.
Can you,
Microphone's coming.
thank you. Can you actually resolve any sort of spectroscopic binaries with periods of a few days or more?
2 days. I'd have to check the numbers. In terms of spatial resolution, we very easily resolve Pluto and Charon. You can see those as a very widely detected. Well, fundamentally, the spatial resolution is about that same HST. The mirror is about the same size, so it's about 0.08 arc seconds. And we can do a bit better than that because we have lots of scans on different scan angles and we can deconvolve it. So we'll get down to about 0.05 arc seconds spatial resolution. So what that means in a binary of a given period depends on the mass of the binaries and the distance of the binaries. But certainly nearby, the number of binary, for example, binary Cepheids, several of the primary calibrators turn out to be binaries, and we've had to throw them out. And so we're discovering a lot more binaries than one might have thought. So Gaia is actually quite good for that. But this is something that we have a special processing unit for, and they haven't even started working yet because we've been busy with these other little challenges. And they start work next year.
Okay, last question.
If I'm loud enough, I'll go. First, from the United States, we're very grateful for Dr. Russell and his contributions. Second, implicit in everything you were talking about was the interactions, and you talked about measuring clusters. Is there going to be any effort to actually look at the interactions with the objects within those clusters?
Oh, yeah, yeah.
At a more precise level, I would assume?
Yeah, no, we can already, because particularly for the nearby clusters, Gaia gives three-dimensional distances and three-dimensional velocities. So we can already map out in 3 dimensions the change in velocity and isotropy as a function of position down the line of sight, because clusters turn out not to be round, and so you need to do it down the line of sight as well as across the line of sight. So we can see that already. And so all these mass segregation, actually I don't think I'm giving away any great secrets by telling you that next year we will be able to tell you that whether the concept of a cluster forming in dynamical equilibrium and then mass segregating is a gross exaggeration. We can already see that just in the velocities and the kinematics. So yeah, it's sort of hard to visualize really, but just taking a cluster like the Hyades, an easy one, already we have three-dimensional velocities with an accuracy of 0.5 kilometre a second for every star. Now the velocity dispersion is 1.5, so we've resolved the peculiar velocity of every star in the Hyades and its distance, and that's just today. You know, we're going to do this across half the galaxy. We're in a whole new realm of data processing and challenging assumptions here.
And the lifetime of the mission?
Well, you'll have to ask Fabio. The default, the minimum lifetime is 5 years from when we started, which was mid-14 to mid-19. There is a proposal going through the SPC process at present to extend that. The engineering lifetime is 10 years. Everything's working fine. In fact, we've been very lucky with the sun not destroying our CCDs. So the physical state of the spacecraft is, as they like to say, nominal. It's just beautiful. So we can go for 10 years, and all we need is the money to run the ground stations. And I think we'll lock Fabio in the room until he says yes.
Okay, I'm afraid we must move on. Gerry, thank you very much.